Hello everyone. In this lecture, we are going to explore a foundational concept in AI that applies not only to games and logic puzzles but also to real world scheduling, planning, and optimization tasks. So, this is the concept of constraint satisfaction problems or CSPs. So, what makes CSP unique is that, unlike other AI search problems that explore unstructured spaces, here we operate under rules, constraints that guide and limit our decisions. So, from timetable generation to Sudoku puzzles, CSPs are everywhere in artificial intelligence applications. So, next, first we'll begin with the general understanding. So, whenever we solve a problem in AI, goal is always to find a path from start state to goal state. But in many situations, we are not free to choose any path. Certain rules and dependencies restrict the way we can move. So, these rules are called constraints. And the problems of this kind are called constraint satisfaction problems. So imagine you are creating a timetable. You can't assign two lectures to the same class at the same time, right? Or schedule two exams in the same room simultaneously. So these rules make the search more intelligent but also more complex. So a CSP is essentially a problem where we search for a solution within boundaries. Okay. So this is CSPs. And then we'll see a CSP consists of certain key components, that is three key components. One is variables. So these are the unknowns we need to assign values to. For example, in Sudoku, each cell is a variable. And domains, each variable has a set of possible values it can take. That is, in Sudoku, the domain for each cell is numbers, each cell numbers is 1 to 9. Okay. And then constraints, so these are the rules that specify which combinations of values are allowed. For Sudoku, a constraint would be no two same numbers in a row, column, or a 3 cross 3 grid. So each constraint is defined over a scope and a relation, uh, that is which combinations are allowed. Okay, this simple structure makes CSPs extremely powerful in modeling a wide variety of problems. Then next, classify the constraints based on how many variables they involve. First is unary constraints. So they involve only a single variable. For example, x must be greater than 3. And then binary constraints. So these are between two variables. For instance, x1 which is not equal to x2. And then global constraints, these involve more than two variables. For example, all variables must have different values. So this is common in puzzles like Sudoku or cryptarithmetic. We'll see that example. So understanding the nature of constraint helps in designing which algorithms to apply and how to represent them efficiently. So next, real world examples of CSP. So CSPs, it is not only just theoretical, they are used to solve practical day-to-day challenges. So first is timetable scheduling, assign classes to rooms and time slots while avoiding the overlaps. And then resource allocation, assign people to jobs, machines to tasks, or vehicles to routes. And then puzzles and games, Sudoku, crossword, logic puzzles. So planning and layout, circuit design, exam planning, even factory workflows. So any situation where multiple options must be assigned under rules and restrictions can be formulated as CSP. Okay. So these are real world CSPs. And then another numerical example. Suppose we want to give rupees 111 using currency notes 2, 5, and 10, and we want the total number of notes to be between 40 and 50. Okay, so we can define between variables, that is number of 2, 5, and 10 notes. Domain will be number of notes for each denomination. Constraints, total sum must be 111. Okay, so total number of nodes must be in the specified range. So this problem can be modeled mathematically and solved using CSP techniques. Right, this is one of the example, and another example is that you can see here it's a crypt arithmetic. So in a problem like a send plus more, which is equal to money, each letter represents a unique digit from 0 to 9. The goal is to assign digits to letters so that the equation holds true here. The variables are the letters, the domain is 0 to 9, and the constraints are no digit repeats across the letters, the arithmetic sum must be correct, leading digits cannot be 0. So this becomes a 10 variable CSP with multiple interlocking constraints, making it ideal for AI modeling, right? And then if we go deeper into this example, the puzzle is broken down into a structure like a long form addition, uh, carryover conditions, positional logic. So this is an excellent case of combining mathematical reasoning with combinatorial constraints. So solving it requires an intelligent search strategy guided by constraint checking. Okay. And then how do we represent the CSP as a search problem? Okay, if you just think of a tree, each level represents a variable. Each node represents a possible value for that variable. A complete path from the root to a leaf, which represents a full assignment of all variables. So here the challenge is to find the paths that satisfy all constraints. So this will be the solution. The tree grows exponentially, so we need the strategies to prune or avoid unnecessary paths. And then so this is another example where room coloring problem. So which has the problem is for kitchen it has a dining room and HS hall, and we have two bedrooms. So master bedroom, storeroom, guest room. So constraint is that what recommendations for the room coloring. Okay, so all bedrooms there will be certain constraints for this problem. Okay, similarly you have the other one. So this is whichever I have explained earlier. This is a search tree generation problem. So when solving a CSP, you don't explore the entire search tree. Instead, we generate only the valid branches. For example, if a certain assignment violates a constraint, we don't need to explore any further down that branch. So this is where constraint propagation and early conflict detection become essential. So they reduce the number of paths we need to explore. Okay. And then we have a backtracking search for CSP. So this is one of the solving techniques, backtracking search. In backtracking, we assign variables one by one. If a constraint is violated, we backtrack, go back to the previous variable and try a different value. So what makes CSP backtracking powerful is that its intelligent is it does not go back level by level blindly. It jumps directly to the variable that caused the conflict. Okay, so this is known as the intelligent backtracking or backjumping. So this is faster than the brute force and is often combined with other strategies like forward checking or and the constraint propagation. Okay. So here constraint satisfaction problems are the problems where we must find variable assignments that satisfy a set of rules and which includes clearly defined variables, domains and constraints. Problems like Sudoku, cryptarithmetic, scheduling and timetabling we have seen. Efficient solving techniques like backtracking, constraint propagation and pruning. So these problems are everywhere in the real world. Learning to model and solve CSPs helps you become better at building intelligent, efficient systems. Okay. So thank you.